At a fireworks celebration, a rocket is launched upward from the ground with an initial velocity of 170 feet per second. The engineers need to know how high and how far the rocket will go before it begins to descend back towards the ground. The formula for vertical motion of an object is h of t equals negative 16t squared plus v times t plus s, where v is the initial velocity and s is the initial height. Time, represented by t, is measured in seconds, and height, represented by h, is measured in feet. What we want to do is write a function that describes the height of the bottle rocket t seconds into the launch. So what do we know about the problem? Well, we do know that the rocket is launched upward from ground with an initial velocity of 170 feet per second. We are also given a template for the vertical motion formula. If we know the initial velocity and the initial height, we could substitute those values into our formula and we'll have a function to model the path of the firework. So do we know the initial velocity? Yes, we do. That's 170 feet per second. So I'm going to substitute 170 in for v in my template. I also know the initial height s because it's being launched from the ground. That means my initial height is 0. With those two things in mind and I substitute them into my pattern, I now have this for my model. And again, the plus 0 at the end of the equation, it's not going to impact the model, so we could omit that too if we want. So either of these two formats would be equivalent forms of the function to model the path of the firework. Now that we have the model, we can use our technology to see the path of the firework and do some evaluations from that. So with that in mind, we can take our model and enter it into our technology, whether it's our graphing calculator or Desmos. Now remember, graphing calculators accept inputs represented by x. So we're just going to have to put this into y1 on our graphing calculators. Desmos folks, you can do the same as well. Now we're talking about a possible window. We have to think about the inputs, right? T, time in seconds, that's x on your calculator. What's the least amount of time that can pass? Well, that would be 0. So to see what's happening at 0, we want to look a little bit to the left of it. So I'm going to start with maybe looking at -2, and we're going to have to estimate how long we think the firework is going to remain in the air for. So again, 60 seconds is a minute. Keep that in mind when you're talking about your possible maximums. I'm going to say maybe 12 seconds, and I'll count by 2 seconds apiece. And I can always adjust this x maximum number to see longer if it's going to remain in the air longer than that. Now the outputs, that's your h of t, right? Your graphing calculator recognizes that as a y. So what's the lowest height it could have? Well, technically that would be at ground level. So I want to see a little bit beyond that on my view screen so I can see what's happening at the ground level. And height, when we're launching fireworks, it's got this velocity of 170 feet per second, it can go pretty high off the ground. So I'm going to have to do an estimate here. Let's say we'll measure about 500 feet above the ground. And let me pick my minimum at maybe -25 feet. And we'll count by 25 feet for my scale. So if I adjust my window on my calculator, Desmos folks, remember yours is in the wrench icon, and you're going to adjust your settings for your x, and you're just doing it horizontally from -2 to 12, and then it says your step, that would be 2. And then for your y's, again, you're going -25 for that minimum. Your maximum is 500. The step would be 25. So with your window fixed either on Desmos or your graphing calculator, you have this as your y1 for your function. We should be able to hit graph and see what results. If we can see the full path of the firework, the window is good to go. No adjustments need to be made. We just want to label what do the inputs represent and what do the outputs represent. So When I hit graph, again, I can see the starting point of the rocket being launched into the air, turning, and how it is coming back down. So I have a good window for my situation. Again, we're labeling the input as time in seconds, the output as our height in feet. Now that we have the model represented, we can start doing some evaluations with it. So our next question said, how high is the bottle rocket 3 seconds into launch? So we're talking about time, and 3 seconds would be about here. So looking at the graph, if my input is 3, I can estimate what its output is. But again, is there a better way to find that result? Well, because we have this function and we're given an input, we could substitute it into the function and see exactly what kind of output we have. So again, by substituting in your value of 3 seconds, we find that the bottle rocket, is 366 feet above the ground 3 seconds into launch. And again, if we check graphically, that seems about correct, because again, counting by 25s, it's 375, it's below that, we're on target. Our next question says, when does the rocket reach the height from number 3 again? So our height of 366 feet. Well, the height, that's an output. And so they're giving us the output of the function. Could we find its other corresponding input? Well, graphically, again, if we drew that line, we can see there's 2 places that it happens at. One's at 3 seconds, but now we're really interested to see at what time is it reaching that height again. So again, by substituting the output into the function, how do we find those inputs? Well, graphically, we can find the intersection of these 2 functions, right? It's a system of equations. One equation is just saying we're looking for outputs of 366. Here's the other function that we have modeling the path of the bottle rocket. We're trying to see when they're equivalent. So again, with graphing calculator, folks, what do you press? We press second trace intersect, and then we'll hit enter 3 times, because it'll ask you for the first curve to register the bottle rocket's model. It'll ask you to register the second curve, which is your output of 366. It'll say, do you want to guess? You don't, press enter, and it will give you the value for the input. As most folks, you could just click on that intersection point and it'll give you the coordinates for that location. So we can see that it's approximately 8 seconds where that happens. And that's if you are rounding to the nearest second. If you're going for the exact value, that would be 7.625. Because there was no specification about if we were rounding or not, I would accept both answers. If you are rounding, use the approximation. I personally would go with the exact value because it's a terminating decimal. But again, this is the process that we can go through to get that. Our next question asked, how high did the rocket go before it descended? When did that occur? So if we think about the rocket is launched here, it's ascending, right? So this is our increasing interval. It gets to this point here, it turns, and now here's our decreasing interval. So this point is our key feature, it's our vertex. So we need to find the coordinates of this vertex. We have a couple of options. Graphing calculator, folks, if you go to second trace and pick option 4 because it's the maximum, we can have the calculator find this value. Once you press that, you're going to see a left bounds. You're going to take your cursor and move it just left of where you think that turning point is and press enter. It'll then say right bound, move the cursor to the right of that turning point and press enter. It'll ask you, do you want to guess? You don't, press enter a 3rd time, and it will give you the values of your vertex. So one way to find it, again with the technology, it will do that for you, second trace maximum. So here we've got 5.3125, a nice terminating decimal, and 451.5625. We're talking about the height, again, that's the output, so it went 451.5625 feet above the ground after 5.3125 seconds from being launched. Desmos folks, you can click on your maximum, and again, it will tell you those coordinates. Now, if you forget how to use your technology to find that point, you do have your algebraic way of finding the vertex, just like when we did graphing our quadratic functions. Remember the pattern x equals the opposite of b over 2a? Well, our b value is 170. Our a value is negative 16. If we substitute those into the pattern, we have the x value for the vertex. We can then take that and substitute it into our function and find its corresponding y value, which again gives you your 451.5625. So you have two methods for solving your values for your vertex, whether you are using the technology or doing it algebraically. And again, the rocket will reach your maximum height of 451.5625 feet after 5.3125 seconds from being launched. Again, I would go with the exact values, but if you are rounding to the nearest tenth, use the term about, and again, you're showing me your work. If you are using the technology, you have the exact values, you should be good to go. And again, algebraically, you can get the exact values as well. But if you are rounding, show me your evidence and use about in your sentence. Our next question is, when did the rocket hit the ground? So as we look at our graph, again, we're trying to see about those key features. We know here, this is where the rocket is launched from. Again, it goes up in the air, gets to this point here, your turning point, the vertex turns and then comes back down. So it's hitting the ground here. This is the point that we are looking for. It's an x-intercept. And we know it's just beyond 10 seconds, so we can kind of use it as a guide as we're doing our solving to make sure we're on target. Well, how can we find that value? It's not a grid value, so reading it off the graph is not going to be helpful. We have an idea of what it should be. How can we find its exact value? Well, it's an output, and so as we did before, we know the output is 0. We have the function for it being modeled. We can find the intersection of the two to see its exact value. So if I enter 0 for my y2 in my graphing calculator or on Desmos, we're going to find the answer to this systems of equations like we've done previously. So again, you're entering in your second function for y equals 0. You're going to see your horizontal line being graphed on your screen. You're going to press second trace graphing calculator, folks, and intersection. So bring your cursor over to this point and you hit enter 3 times. Desmos folks, you are going to click on that intersection point and the values will be revealed to you. And we can see that we end up at 10.625, 0. That's the location of this point. So when does it hit the ground? It'll hit the ground after being in the air for 10.625 seconds. Again, I would go with the exact value. If you are rounding to the nearest tenth and you said about 10.6, that's fine. You have the evidence shown to support your work. Our next question asks, what's a reasonable domain and range for the situation? Well, if we're able to set our window and see the path of the rocket, we can use that to help write our domain and range. Domain is a set of all the inputs, and again, it's for the situation. So what makes sense for our domain? Well, definitely when the rocket is being launched, right, for time of 0 until it lands. And again, we found this point in our last problem. So we could say a reasonable domain would be from 0, including 0, to 10.625. Because that is the time that the rocket is in play, launched and landed. Now for the range, they're talking about the lowest height it can reach to the highest height it can reach. So for the range, we know the lowest it can be is 0. And the highest, well, that would come from the y value of your vertex. Let me draw that line a little bit better there for us. So again, what was that value? It was 451.5625. Now, if you did do rounding for each of these and you said it was in play for 10.6 seconds and you put your bracket there, I would understand why you did that. That would be okay. If you said this was 451.6 and you put your bracket, I would understand based on your previous responses. But again, we're looking to see what is the minimum maximum values for the inputs being used for the rocket launch situation, not just the general function. So we're narrowing it down versus just it in general, how is it behaving? Same thing for the outputs. And our last question says, suppose the bottle rocket is not launched from the ground, but from a 200-foot tall building instead. How would that change the function? So let's think about this. Where did our function represent from the ground? Well, that was the part at the end here where it was the plus s, right? So we technically had the plus 0 here. So if we're not launching it from the ground, we're launching it now from a 200-foot tall building, that's going to change our function. So here we would have to add 200 to the back of our equation, because again, that number was represented by an s, talked about the initial height. So our function would look like this, negative 16t squared plus 170t plus 200. So what is that going to be doing to the function? Well, if we're raising everything up 200, it's a vertical shift. So remember here, it started at the ground at 0. Now it's starting at 200 feet above the ground. Everything was shifted up 200 units from where it was previously. So again, it's changing the function by changing our initial height. It's a vertical shift up 200 feet. Now notice by shifting it up 200 feet, it also prolongs how long the rocket is in the air, because we said it landed here at that 10.625. Notice how it prolongs the flight just short of 12 seconds. And again, we could calculate that by doing the intersection of our second function of 0 with our current model to see how that happens. But again, big idea is shifting everything up 200 units, and by doing so, it will prolong the flight of our bottle rocket.